This is 5.1, 5.2, part 2, and this is basically where we left off in class. So I'm going to finish this section so that way you guys are able to do your homework. So example number 3. Suppose a particle is moving along a line with changing velocity and we want to estimate the total distance traveled over a 12-second time interval. Velocity readings are taken every 2 seconds and are recorded. So if we look at the time, which is S, we see that we're going from 0 to 2, 2 to 4, 4 to 6, 6 to 8, and 8 to 10. So what I'm going to do is I'm going to make the width of each of the rectangles equal 2. And we know that because that's when the readings were taken. So I have this situation going on right at the moment. Then it says a velocity that corresponds with each of the times are 10, 15, 21, 23, 26, 22, and 18. So it says to estimate the distance traveled by the particle using the left endpoint values. Okay, so the left endpoint values, I'm going to look at 0 first. And I'm going to draw the rest of the triangle out. So here is 0. So here's our first rectangle. So the left endpoint would be at 2, would be the next one. The next one would be at 4. The next one would be at 6. The next one would be at 8. And the last one would be at 10. So here is what my rectangles look like. So I need to do... Remember, we're summing. We're taking the summation from the interval 1 to the interval 1, 2, 3, 4, 5, 6 regions. So that's going to be sigma going to 6. And then we're doing delta x. And remember, we're taking the endpoint, or x sub L. Because... Sorry guys, I'm trying to write this up and I have a new eye pencil. So this is causing a little bit of troubles. So remember the left is I minus 1. Okay, so let's go ahead and do this. Delta x, we know is the width, and the width of each of these intervals is 2. Okay, so what I'm going to do is I'm going to take 2 times the function at 0, because that's my first left endpoint, plus the function at 2, plus the function at 4, plus the function at 6, plus the function at 8, plus the function at 10. And that will be my last one. Alright, so this becomes 2 times. The function at 0, if you look at the chart, it's 10. So I'm going to put 10 there. The function at 2 is 15. The function at 4 is 21. The function at 6 is 23. The function at 8 is 26, and the function at 10 is 22. So what I'm going to do is I'm going to add those all up and multiply it by 2. I'm going to take out the calculator and do that. So I get 10 plus 15 plus 21 plus 23 plus 26 plus 22. And when we do that, we get 117. And I'm going to multiply that by 2. To get 234. And remember, this is estimate the distance traveled by the particle, and the distance traveled would be I'm trying to see what it is, seconds, feet per seconds. So feet per second. Okay, all right, so let's do this next one. Boat has sprung a leak. Water is flowing into the boat at a rate as given as follows. The time is in 5-second increments, or 5-minute increments, excuse me. So I'm going to go ahead and partition each of these data values on the chart into 5-minute intervals. Okay, so right now I know the width of these rectangular regions is going to be 5. So delta x is 5. So we know that. Okay, now I'm looking at the results in the chart, and it says at 0 it's 12, at 5 it's 20, at 10 it's 24, At 15, it's 16, and at 20, it's 12. Estimate the volume of water that has flowed into the boat during the 20 minutes using the right endpoint values. Okay, so the first right endpoint for the first rectangular region would be 5. So this rectangle looks like this. And then the next one's going to be 10. The next one's going to be 15. And finally, the last one's going to be 20 using right endpoints. So I'm going to take delta x, and then I'm going to multiply that by the function at 5 plus the function at 10 plus the function at 15 plus the function at 20. Again, I'm using these values because I have to use the right endpoints. So I'm just making those bigger. Okay? All right, so delta x was 5. And the function at 5, I'm going to look up at the chart. It says it's 20. Plus the function at 10 is 24. Plus the function at 15 is 16. The function at 20 is 12. So again, I'm going to add 20 plus 24 plus 16 plus 12. So I'm adding whatever's inside the parentheses first. And I got 72. And I'm going to multiply that by 5. So I get 360. And the rate is liters per minute. Okay? All right, so as you can see, if you make rectangular regions under a curve, you're able to estimate what that area is. If we go down here, and I'm just going to talk about part A here, there's a chart. So it says the area is approximately equal to the summation of a regions from 1 to n of the function at x sub I. Remember, it could be x sub I minus 1 representing left endpoint. X sub I is the right endpoint, and then x mid, mi, would be the middle point. And then we're multiplying that by delta x. Okay? So if you look at the chart, it's just showing you we have the function x squared on the interval from 0 to 5. And the area under the curve was calculated using the left endpoints, the right endpoints, and the middle endpoints. So if you look at the chart, the more rectangular regions we get, and that's what n is, by the way, the rectangular regions, this right here, as it increases, we see that our values using left, right, or middle almost become the same. And remember when I told you in class before that if you use the middle point, that is the most accurate, because look at that. If I'm just using 5, so I'm using 5, I got 41.25 right out of the gate. The answer, or the closest answer, is 41.6. Right? So that's pretty darn close, considering we're only using a small amount of regions, or rectangular regions. The left at 5 was only 30, and the right was 55. So again, left endpoints, if you have a small number of them, is going to give an underestimation. If you have a small number of rectangular regions, and you're using the right, you're going to get an overestimation. But that calms down the more rectangular regions you have. So we see that the left, when we have 1,000 rectangular regions, we get 41.604. For the right, we have 41.729. And for the middle, we have 41.667. So those pretty much equal out once the approximations improve as n increases. So in other words, the more rectangular regions we use, the better off we get an estimate. Doesn't matter what I'm using. Again, though, the midpoint approximation is the most accurate. Or I should say, it's more accurate than the left and right endpoint approximations. Okay, I'm skipping B. We're not doing that. So I'm just letting you know that thank you for watching the video, and that is the end of 5.1, 5.2.